All right, in this lesson, we are going to be talking about transformations and key features of the square root parent function. Okay, so the square root parent function is f of x equals square root of x. To see what this graph looks like, we're going to plug in points. And so when we're picking points to plug in, we want to pick perfect squares. So for example, 0, I can take the square root of 0 and get 0. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. And so that means I have the point 0, 0, I have the point 1, 1, I have the point 4, 2, the point 9, 3, and so I can go ahead and graph those points. Okay, and then if I try to plug in -4, square root of -4 is an imaginary number. And so it's not going to show up on the graph. And so anytime you try to take the square root of a negative, it's not real. And so our function kind of has this blunt stopping point or starting point at 0. And so to identify the domain, 0 is the smallest number we can plug into this function, and then we can plug in infinitely large numbers. And so you can see on the graph, it starts at 0 and goes to the right. And so our domain is 0 to infinity. Our range is the same thing. We're not going to get negative outputs. We're starting at 0 on the y, and it's going up. And so our range is also 0 to infinity. And notice I'm using a bracket for this interval notation because we do equal to 0. It's not a whole, it's not an asymptote situation. And so we do want to use a bracket instead of a parenthesis. Okay, over here, transformation form looks like this. We have a scale factor outside the radical. We have a scale factor inside the radical. And then we also are adding and subtracting numbers inside and outside. And so the scale factor outside the radical, that's where you're going to get your vertical reflection. And so that's your reflection over the x-axis. And that's also where you're going to get your vertical stretch or your vertical compression. Okay, and so a vertical reflection would end up with a square root that looks upside down. And then, of course, a stretch would be taller, and then a compression would just be shorter. For the b value, that is where we have our horizontal stretches and compressions and reflections. And so I'm going to say horizontal reflection, which would be a reflection across the y-axis. And that would cause our square root function to be facing to the left. And then a horizontal stretch or compression. Something else to notice, whenever you're inside the function, so for us under the radical, everything's opposite. So a fraction here would be a stretch, and then a whole number would be compression. Large numbers would be compressions. The easier transformations are the shifts left and right, up and down. So this would be left and right, and this would be up and down. Okay, and so in order to graph using transformations, another thing you want to notice about our parent function is the relationship between the points. We go up 1 over 1, up 1 over 3, up 1 over 5, if we're talking about the distance between the points. So my change in y values, the distance between our y's is always 1, and then the distance between our x's goes 1, 3, 5. That'll help us graph our stretches and compressions to notice that pattern. All right, for this first example, the first thing I want to do is list the transformations. So I am seeing a +4 under the radical and then a -3 outside the radical. Anything under the radical happens in the horizontal direction and it's opposite. So this is left 4 and then the -3 outside is down 3. Okay, so graphing our parent function, we have 0, 0, 1, 1, 4, 2, and then 9, 3. So to move this left 4 and down 3, it takes the origin, that starting point at 0, 0, and we go left 4 and then down 3. Okay, and so we can see our new starting point is here at -4, -3. So you can kind of treat this like vertex form of a quadratic. And then we can see our x-intercept here is at 5, 0. Okay, and so x-intercept is 5, 0. And then increasing, this function is either always increasing or always decreasing. And so looking at our graph, it is going up and continuously goes up. It's going to keep going up. And so our function is going to be increasing over the entire domain. So from that -4 where we started, all the way to infinity, which is the entire domain. Okay, for this next graph, I have a 3 as a scale factor outside, and then notice the square root ends, and then this +1 is outside the square root. Okay, and so this would be my vertical stretch by 3, and then that +1 would be up 1. Okay, and so once again, graphing the parent function, we have 0, 0, 1, 1, 4, 2, 9, 3. I'm going to shift it up 1. So now we have our starting point at 0, 1. And then to do the vertical stretch by 3, remember the pattern of our points goes up 1, up 1, up 1 between all of our good points. And so now instead of going up 1 each time, we're going to go up 3 to get our next point, up 3 to get our next point, and then up 3 to get our last point. So here's our vertical stretch. It looks a little bit taller. Okay, and so here's our new function. And so 0 is another name for x-intercept. Usually if they're talking about it as an x-intercept, they write the ordered pair. When they talk about it as a 0, they typically just write the value. But here, we don't ever cross the x-axis, and so there is none. For the domain, our x starts at 0 and it's going to the right. And so this function has a domain from 0 to infinity with a bracket. Okay, moving on, the first thing I want you to notice is that we don't have proper transformation form. Up here, you see when I have a b value and an h value, there's a set of parentheses. And so if you don't see parentheses here, you need to add them and factor this 4 out. So what you do is add a set of parentheses and then divide this h value by whatever b is. So the equivalent form of this expression would have a 4 and then an x plus 4. And so these are algebraically equivalent. If you were to type these in to your calculator, you would see identical graphs because they're the same function. Here, you can't read the transformations, but in this second form, you can. So you have to be very, very careful to make sure you have proper form. Okay. The other thing I want to point out is that if you have a scale factor under the radical, if it's a perfect square, you can actually take it outside the radical and view it as a vertical transformation rather than a horizontal. And so another way we could write that is the square root of 4 is 2, and then we would just have the x plus 4 inside. Okay, and so if I'm reading the transformation, this would be a horizontal compression by 1/4. Which is incredibly hard to graph. And so it is easier to view it as a vertical stretch by 2. Both are going to result in a taller, thinner graph, but the scale factor changes when you factor it out of the radical. Okay, one is just easier to graph. Okay, And so I am going to graph the reflection across the x-axis. I'm going to call that a vertical reflection. Also known as a reflection across the x-axis. We're going to vertically stretch by 2, and then we are also going to move left 4. Okay, and so I'm going to put the parent function 0, 0, 1, 1, 4, 2, and then 9, 3. Okay, so the first thing I'm going to do is shift the graph to the left 4 so that we can see what our new starting point is at -4, 0. And then it is also reflected across the x-axis. And so all of my y values are going to be below the axis. So instead of 3, it's at -3. So here's our reflection. And then the only thing we haven't done so far is our vertical stretch by 2. So just like the last example, instead of going up 1 between our points each time, we're going to go up 2. Okay, and so this starting point stays, but now I'm going up 2 to get to my next point, up 2 more to get to my other point. And then up 2 more, actually, yeah, up 2 more to get to my last point. So remember, the starting point stays where it's at, and then we just stretch all the y values to be 2 instead of 1. Okay, and so there's our vertically stretched and reflected and moved left graph. And so this time our range, it's going from 0 to -infinity because it's going down. And so how we write that is from least to greatest. So bottom to top, -infinity, and then we stop at 0, which would be the maximum for this function. And then our y-intercept we can see is at 0, -4. Okay, so in these last examples, we are actually given the graph and we are going to write the equation. And so I like to put some good points if they're not given. And so here I can see my starting point is at 5, -6. And so that means my function moved right 5 and down 6, because usually that should be 0, 0. Right 5 and down 6. If I put some other good points on this graph, I can see that we have a point that is up 3 over 1. Okay, and then we go up 3 over 3, and then we go up 3 over 5. And so my x distances are still following that 1, 3, 5 pattern, except the y's are now 3 apart instead of 1. So that tells me there is a vertical stretch by 3. Okay, so 3 transformations. And so we're starting with the square root function. To move right 5, we subtract 5 under the radical. To move down 6, we subtract 6 outside the radical. And then to vertically stretch by 3, we need a scale factor of 3 in front of the radical. Okay, for this next example, I can see my starting point is at -7, -4. And so that means I moved left 7, down 4. Okay, and then I see that it's also upside down, so that means there was a reflection across the x-axis, a vertical reflection. And then putting the other points on the graph, I can see I'm going down 1 over 1. If I go down 1 more, I go over 3. Down 1 more, I'm going over 5. Okay, and so our pattern, our 1, 3, 5, and our 1, 1, 1 pattern is still the same. So there is no stretch or compression, just that reflection. So to write my equation, I have a left 7, so plus 7 under the radical, a down 4, so minus 4 outside the radical. And then for that vertical reflection, your negative goes in front of the radical. All right, looking at this last example, we have a starting point at 0, 0. And it is still at 0, 0, so it hasn't been moved left, right, up, or down. But it is facing to the left this time, and so that tells me there is a horizontal reflection, a reflection across the y-axis. Okay, and so to see our stretch or compression, we have this other point here, and so usually our y distances go up by 1s, and this time it's going up by 3. Okay, and then our x distance is usually 1 for our first point, and this time it is 4. So I see that there is a vertical stretch by 3, but also a horizontal stretch by 4. Okay, and so to put that in an equation, we're going to have our square root sign. And then our vertical stretch by 3 is going to have a scale factor of 3 outside. And then our horizontal stretch by 4 is going to have a 1/4 scale factor under the radical. Okay, and then we also have that horizontal reflection, so that 4 would be negative.